Aha, so another one. So in theory, everybody did the equilibrium and kinetic activity. And the first part of this presentation is about the last part of that activity. Okay, so I gave you a couple of things about the Haber-Bosch process, that is to do fertilizers, to do ammonia, NH3. So the reaction is nitrogen, molecular nitrogen, plus 3 molecules of hydrogen gives you 2 molecules of ammonia, right? And that one is a exothermic reaction with a minus 92 kilojoules per mole. Okay, so that is the first part. If you see that particular reaction, only with that reaction, knowing that the reaction is exothermic, you can tell a couple of things. For example, how to shift the equilibrium of that reaction. For example, if you add reagents, of course, because of the Le Chatelier principle, you're going to shift the equilibrium to the product. Okay, and there are other ways. For example, if you compress that reaction, because you have 4 moles of gas in the reactants and 2 moles of gas in the products, the equilibrium will shift to the products because they have more space to interact with each other, right? Or you can see it like if you compress the system, well, the gases, if you have more moles of gas, they're going to be closer together and they're going to be able to react easily, right? So in that reaction, if you put a high pressure, you're going to shift the equilibrium to the products. That is, of course, the objective. And in the case of the enthalpy, well, in the case of the enthalpy of reaction, that is an exothermic reaction, what you need to do is to take heat away from the reaction, because this reaction is going to produce heat, right? So we could write down here like a term of heat, right? Okay, that term of heat, it behaves the same way as a reactant or a product. If we raise that the heat, the reaction is going to shift to the reactants instead of the products. Okay, so what we need to do in this reaction is to have a lower temperature, right? To shift the equilibrium to the products. Okay, and then I gave you a lot of physical properties about these 3 gases, the reactants and the products. So the molar mass, the fusion temperature, the boiling point, the density, the triple point, the temperature and the pressure at which you obtain the triple point, and the critical point. Okay, and the magnetic order. The magnetic order was just for fun. You don't need it for this particular process. But what you can see is that if you have for example, if you have these 3 gases, one way of separating them is through temperature. If you lower the temperature of the system below 239 Kelvin, well, you're going to obtain liquid ammonia, right? And hydrogen and nitrogen will keep as a gas, right? Because we have boiling points that are a lot higher than the boiling point of ammonia, right? So that's exactly what we are going to do in a process. So let me talk about a little bit about kinetics. In an industrial process, for example, in a lab, maybe the most important part is the equilibrium. So low temperatures, high pressures, and we obtain a good yield of the products. But if we have an industrial process, the yield is not all, right? We have to pay attention to the kinetic of it. And in the kinetic, well, the kinetic behave the same way for all reactions. High temperatures and high pressures give you the best, well, the highest rate of reaction. Okay, so if you see in equilibrium, well, we are saying that low temperatures, but in kinetics, we need high temperatures. So we have to do a balance of those 2 things to obtain equilibrium in the process and to obtain a good amount or a good yield of the product, but in a time that is interesting for the process, right? To sell it like a fertilizer, for example. Okay, so there is another plot where we can see if the assumptions that we're doing are correct or not. Here we have the pressure in the bottom. We have the percentage of conversion. So you see that if you raise the temperature, you have 500 degrees. That is the lowest temperature in this plot. You have a high conversion of ammonia, around 95, 97%, right? But if you raise that temperature, the percentage of conversion starts to drop dramatically, right? We pass from 95 to around 10% at 900 Kelvin, okay? So, and we can see the relation with the pressure too, right? If we have low pressures, we have a low equilibrium, right? But if we start raising the pressure, we're going to start seeing yields of higher order, right? For any temperature, okay? So, like I said, in equilibrium, we said we need high pressures and low temperatures. Low temperatures, the lowest that the process permits, right? And in kinetics, as high pressure as we can, and as high temperature as we can. Okay. So the whole point of the activity, the last part of the activity, was for you to reach to these kind of conditions, to say we need a high pressure, low temperature for equilibrium, and high pressure, high temperature for kinetics. And then seeing that, understanding that there is a equilibrium in the speed that you're going to obtain the product and the yield of that product. Okay, so then to propose a process, right? And in this case, the best way to do it, well, the way we do it right now in new plants, is to do something similar to this. Okay, so what we have here is the reactor. The reactor is this gigantic thing, right? So there we fed nitrogen and hydrogen in gas after processing those gases and to clean them up. And we pass them through a compressor to raise the pressure of the gases. Those gases go into reactor that has a catalyst bed that raises the speed of that reaction. They react and they form the product, NH3, and a lot of unreacted nitrogen and hydrogen gases. So those, we pass them through a heat exchanger when we reduce the temperature of the gases, and then we pass them through a condenser when we reduce the temperature further until we have like 80, 260 Kelvin and so on. So in that temperature, the NH3 liquefies or condensed, and we can obtain it into a refrigerated unit, right, underneath. And all the gases that didn't react, because they are gases and they have a low density, we can recycle them to the reactor. So we pass them again to a compressor. In that compressor, we exchange the heat from the products of the reactor and this recycle stream. So we gain energy in that heat exchanger without using without using further energy, right? We have the energy of the reaction, and that's it, right? And those recycle nitrogen and hydrogen that are hot, they return to the reactor and they react further, right? So what the numbers that we have in this kind of process is that in the main reactor we have around 20% of conversion, only 20% of conversion, but it's a fast conversion. Okay, so we can obtain liters, thousands of liters per day using this 20%. But the global conversion is around 95% of the reactants. Okay, and this is using the kinetics and the equilibrium, right? If we don't know that part, we can't understand how to do a process like this one. There are many reactions where you have an endothermic process, so you can raise the temperature as high as you want to and the pressure too, right? But in this particular case, you can't do that because then you would obtain, maybe a very good yield, like 95%, but you would obtain 1 liter a day, right? And that is not the objective of an industrial process. Okay, so that was that activity for you to understand that kind of things. Okay, just a little image or a little bit of thoughts, like to think about all your stuff. This is a plot of the year, right? year, and this is the populations in billions of people, right? So thousands of millions, because Americans use billions in other way that we do. So in this particular part, you can see where the Haber-Bosch process was invented. From there on, the production of food, of crops, has raised like crazy, because it's very easy to do, well, to have a fertilizer, and without fertilizer to obtain a lot of product, a lot of crops. Okay, so if you see this turquoise line, it says more developed countries, right? If you see the population in those countries has raised, but not too much, right? And if you see from the 2000 on, it's almost a constant population, right? But in less developed countries where the food was scarce, would be before the Haber-Bosch process was invented, now we have means to produce food for anybody, right? We waste a lot of food in this planet because nobody eats it when we have more than we can use. And if you see that the population in the less developed countries has raised thousands, right? And there's a big step in this way, right? It's a big step of people in the planet because of that particular process, right? And it's a kind of ironic, funny thing that the guy that invented this process, that he was a Nazi, a German, well, Haber, he wanted to use it like a bomb, like the ammonia in concentrated amount can be used as an explosive. So he wanted to use it to kill people, and well, he turned around completely. And now it has saved hundreds of thousands of people because we can feed them, right? So that is that particular part of the process, and we need that information about the equilibriums and kinetics, because well, the gasification process has many reactions that we need to control or to balance, to obtain the best production of hydrogen and carbon monoxide. That is the products that we want for in the gasification. So we're going to go to gasification, right? So let me take this way around. Okay, so in this figure, you can see how all these processes, pyrolysis, gasification, and combustion, are seen in a match, right? When we run a match, we have all these processes: the pyrolysis, the gasification, and the combustion, right? So the first products that we have is oil vapors and gases around 400 degrees underneath here, right? That is part of the pyrolysis of wood. In that space, we don't have well, we have absence of oxygen, because oxygen can't come in from the ambient, right, through that part. So we have almost zero oxygen. So in this case, the wood start to when we raise the temperature, the wood starts to decompose in oils and vapors, and then those oils and vapors crack down to in higher temperatures, around 600 degrees, and then we obtain hydrocarbons and tar. Tar is like a gooey thingy, almost, well, it's a carbon compound that it's like chapopote style, more or less, like that. And when the temperature raises a little bit more, these oils and vapor can start combusting, and around 1000 Celsius, well, they start to be luminescent, right? That's the part of the flame that we see in orange. And at higher temperature, at around 1500 Celsius, we obtain the combustion of those gases, right? And in the combustions, of course, we combust the gases, the tar, and the soot, that is the fine carbon that you have. Is like a very fine powder that can combust too. And here the combustion products, well, of course, if we have a good combustion, we'll obtain CO2 and water, right? Okay. So this is the combustion process, okay? And most of the biomass burns in this way, anything that you burn, right? But we don't want to do the combustion of this in the gasification. What we want to obtain is hydrogen hydrogen and carbon monoxide to use them as fuel afterwards. Okay, that's the principal objective. So the way we can do that, let me go this out. The way we can do that is by inversing this process. This is the natural process, right? This is the natural process when we burn a wood in this case. But if we want to obtain hydrogen and carbon monoxide, we have to do a little thing a little bit differently. Okay, so what we do at the beginning is to dry the biomass, right? For that, we need temperatures around 100 to 150 Celsius. And that dry biomass, in absence of oxygen, is going to start the pyrolysis, right? The pyrolysis process is the second step. That is around 100 to 500 Celsius, okay? And then we're going to produce charcoal and tar and gases, and those gases are going to combust. We're going to have a place in the device that is going to allow the combustion. So we're going to have more oxygen in that particular place, okay? And in that combustion, well, because of higher temperatures, the different biomass or the different components or compounds are going to start cracking or decomposing in different, well, in their constituents. So hydrogen, water, carbon dioxide, and so on, okay? And then we're going to, instead of having the reduction over here in this place of the natural process, we're going to have the reduction. So we're going to pass the CO2 that was formed, right? And the carbon that was formed to hydrogen and carbon monoxide. Let me address in the chat. Okay. Okay, let me finish and I'm gonna answer you, Ian. Okay, so if we do that, we're going to obtain the cracked gases, that is charcoal, water, and carbon dioxide. With high energy, like 600 to 900 degrees, and a reduction of oxygen. Okay, so absence of, not complete absence of oxygen, because then we would have pyrolysis, but a little bit of oxygen. We're going to start cracking this water and carbon monoxide into hydrogen, carbon monoxide, right? Okay, so Ian told me, how can you ensure a real system that combustion is complete? Okay, so depends on the system that you have. For example, when we use liquid fuels and gas fuels, usually we can mix them completely or mix them in a proper way with oxygen to obtain a complete combustion. But if we have solid fuels like carbon but in chunks, or wood, or leaves, or that kind of things, it's a lot harder to do it, because oxygen is not going to be able to reach all the biomass at the same time to combust completely, even if we have an excess of oxygen. Okay, if you remember when we saw the burners, they use coal, right? They use coal, but they crack it down into a fine powder, so they can release it almost as a aerosol, right? So if you have a solid or aerosol form, you can do the complete reaction easily, right? But if you have a solid fuel like chunks of wood or chunks of carbon, then it's very difficult to have a complete combustion. And the last one is, how can we realize if it's not a complete combustion? Well, many times it's you can see it in the temperature of the flame. But in that part, for that to be so, if you know that a process has a complete combustion and you don't know if it's starting to burn incompletely, what you can do is to compare the temperatures, for example, in the chimney gases, because when you burn to incomplete combustion, you obtain less heat than if you do a complete combustion. So you're going to obtain a lower temperature. But that only works if you have a process that you know already, right? If you have a new system, well, you have to do a gases analysis for that. because CO and carbon dioxide, well, they behave almost identically, right? They are, you can consider them ideal gases, they don't have color, and so on. Okay, one way to do it is the ORSAT analysis, that is the dilution of gases to obtain acids, and with those acids to titrate them and to obtain the concentrations of the gases in the beginning, something like that. Well, now on there are sensors that they use piezoelectric materials, and the difference in conduction can give you the amount of one of the components. Okay, so any other questions before we continue? Okay, so the main products of this degasification are going to be the gases that we want, so the produced gases, and some ash, right? That is full with char, that it's carbon in very small particles, but that carbon can be burned again. Okay, the properties don't allow it to. Okay, so this would be the four processes in the gasification. Okay, not in particular order, just the process. Okay, so the first process, as we said, is drying. Okay, for that one, we can use, if you're going to use a biomass, for example, you could use the sun, or you can use a stream of air, of hot air, to dry it. And of course, then the only thing we're going to have, well, is the biomass. That's going to be this green thing, this green over here, and we're going to put heat on it, and we're going to obtain as a product just water. Okay, just evaporated water. The other process is pyrolysis, that you know a little bit already, that we heat the biomass but without air. And if we do that, we're going to obtain charcoals that are, well, hydrocarbons, very heavy hydrocarbons, and tar that are like more or less the same thing. One is more gooier than the other one. One is more solid. The tar one is more solid. And in that one, okay, you heat the biomass, and that's it. Then we have the combustion, that you know almost all about it. In this case, what we heat is the gases after the pyrolysis, the tarry gases or the charcoal. We heat those and we oxidize them completely to water and to carbon dioxide. And in the case of the reduction, that is the reaction that we are going to seek, is to take the CO2 and the water that go out of the combustion, and through using less oxygen, right, to obtain hydrogen and carbon monoxide. Okay, there are advantages of doing this process. For example, what you can do is to use part of the energy to produce heat, for example, and the other part is going to be chemical energy, right? That is going to be stored in the hydrogen and carbon monoxide. Those hydrogen and carbon monoxide, you can make them react. You can make them react doing a combustion, and you can obtain energy again. And these gases are, well, a little bit more cleaner than just using hydrocarbons. Okay, so you take out the contaminants of some of the gases, and you can use them again. Okay, so that's part of the things that we want to do in the gasification. Okay, so now we're going to see the reactions, and I need you to pay attention to the amount of moles of gases that you have in each side, and what kind of reaction it is, if it's an exothermic reaction or it's an endothermic reaction. Okay, that will be useful when we see how the gasification process depends on the pressure, temperature, and so on. Okay, so the first three reactions are the combustion reactions of carbon monoxide, and hydrogen. Okay, all those reactions, because those are combustion reactions, we are obtaining energy, right? Those are exothermic reactions. That's why all the enthalpies are negative in these processes. And we obtain the oxidations of carbon monoxide to carbon dioxide, from carbon to carbon monoxide, and from hydrogen to water, right? Those are the combustion reactions. then we have the boudoir reaction. That is the conversion of carbon and carbon dioxide into carbon monoxide. That is the product gas that we want to, right? This reaction is endothermic. That's why it has the plus sign on it. And for that one, we need energy. That's why in the process that I talked to you about, the gasification, we're using the energy of the combustion to fuel this to fuel these reactions, this reduction reaction that we're going to happen. Okay, that's why we need the combustion at the beginning. Okay, so a couple of things about the combustion reactions. If you pay attention to all the stoichiometric relations that we have, all reactions, all these three reactions of combustions are, if we want to shift the equilibrium to the right, we need high pressure, right? So we need high pressure because we have less moles of gas in the products than in the reactants. Okay, in most of them we have 1.5 moles of gas in one side and 1 mole of gas in the other, right? So if we raise the pressure, we're going to have higher yields of the products. And if we lower the temperature, because although those reactions are exothermic, we are going to shift the product. We're going to shift the reaction to the products, right? This is to shift the products. Okay. And what happens in the boudoir reaction? This one is an endothermic reaction. Okay. Okay. So in an endothermic reaction, to shift the reaction to the products, we need high temperatures, right? We need to raise the temperature to give energy to the reaction for the reaction to happen, right? And for the pressure, in this case, it doesn't matter at all because we have 2 moles of gas in one side in the reactants and 2 moles of gas in the products. So if we shift the pressure, it's not going to do much in that particular reaction. There's another reaction that is called the water shift reaction. It's called the water shift because we're changing this water to carbon monoxide and hydrogen gas. Okay. If you see the reaction that is endothermic and that we have again 2 moles of gas in one side of the reaction, 1 for carbon and 1 for water, and 1 for carbon monoxide and 1 for hydrogen, then we have equal amounts of gases in both sides of the reaction. So the pressure doesn't affect, but the temperature does, right? So if we raise the temperature, we're going to obtain, well, higher amounts of carbon monoxide and hydrogen. That are the ones that we need, right? And the last reaction is the methane reaction. If we have carbon present, that we're going to have carbon present because the biomass degrades into tar, that is carbon, and hydrogen, we can produce methane. Okay, this methane over here. But we don't want that methane. Okay, so we're going to do a couple of things about it in a couple of slides. Okay, so this particular case, again, because we have only 1 mole of gas in the products and 3 moles of gas in the reactants, if we raise the pressure, we're going to shift the reaction to the products. And if we have an exothermic reaction, so again, if we lower that temperature, we're going to produce, well, highest amounts of methane, right? So if you see, the 2 reactions that we want are these 2 over here. Okay. So it appears that we need high temperatures to do it, right? High temperatures to promote the reduction reactions and to disencourage the reactions that we don't want, like producing methane. Okay, so it's a balance between all those reactions. Okay, so the reactions that we need is the two most important reactions is a mixture of reactions. So this one over here, number 1, reaction number 1, is a mixture of these is a combination of A and B reactions. Okay, so if we inverse this reaction, if we inverse reaction B, right? So we invert it, we're going to cancel carbons on both sides. We're going to cancel one molecule of CO2, of CO, and we're going to obtain the hydrogen, right? So that's the first reaction. And the one with methane is C and B, right? C and B, water shift reaction, and the methane reaction. Again, if you inverse this reaction, the C reaction, and you do the addition with the B reaction, you're going to obtain this one over here. Okay, so those are the two principal reactions that we're going to pay attention to it. Okay, so one is exothermic and the other one is endothermic, right? So depends on what you want to produce. It's how you would want to do the shift. Well, how this reaction should proceed, right? How should be the equilibrium of them. Okay, so if you want a higher amount of hydrogen, it's better to give priority to the reaction, to the second reaction. If you want more amount of carbon monoxide, it's better to give more interest or to the reaction one, right? Because these two reactions, they behave in different ways, right? To shift to products. To products, we will need, for the first reaction, that is exothermic, we would need lower temperatures, right? And the pressure, it doesn't matter because we have the same amount of moles, right? So pressure, it doesn't matter, right? And in the case of the second reaction, on the methane to carbon monoxide and hydrogen, we need high temperatures because it's an endothermic reaction. And again, the pressure doesn't matter too much, okay, for the equilibrium part of it. But what happens to the kinetics of the reaction? If you have high pressures, you obtain a higher rate, right? So the main equilibrium occurs between the partial combustion reaction and the water shift reaction. That's the two reactions that we have to balance all over, right? And the incomplete reaction for any fuel is the one that it's written there. N number of carbons in a biomass and M atoms of hydrogen in that biomass reacts with N/2 moles of oxygen to form N number of moles of CO and M/2 moles of hydrogen gas. Okay. And one interesting thing is that at high temperatures, only methane can endure as a fuel. For example, if you take octane into combustion, the only part that could endure is the methane. All other parts of the fuel will break into different pieces, right? We break down into the small parts of the fuel. Okay. Okay, so as we said, this is the principal reaction. I think that one is no. Sorry. So if you remember how to obtain the rate of a reaction, well, you need the constant rate of the reaction, in this case Kf. And for this reaction, we're only going to pay attention for the reactants, right? So we're going to have the reaction constant times the concentration of carbon monoxide times the concentration of water, right? And for the inverse, for the rate of the reverse reaction or inverse reaction, is the other way around. We have the reverse rate. It's equal to the constant rate of the reaction times the concentration of carbon dioxide times the concentration of hydrogen. Where we get Kf's from, it says here. Okay, the Kf's, or the constant for the rates of the reactions, the only way to obtain those is through experimentation. We have to do experiments with kinetics in mind to obtain these values and to obtain the order of the reaction too. There are molecular models to model these kind of things of kinetics, but they are not as reliable as we hope, not just yet. So it's better to do an experiment or to do a pilot plant to obtain those values. Okay. But for these reactions are well studied. You can find these values in the literature at different temperatures. Okay, so that's not a big deal. Okay, and then we have the constant of equilibrium, right? The constant of equilibrium, if you remember, is the concentrations of the products elevated at the stoichiometric coefficient of each one. In this case, 1 for all the species, times the concentration of the other products divided by the concentration of the reactants, again elevated to the stoichiometric coefficients, and that's it, right? Or you can see it as as a fraction of the different constants of the reaction, of the rate of the reaction. Okay, because in an equilibrium you have two reactions that have the same speed, right? The same speed, but not the same constant. Okay, so that's why we can have the constant of equilibrium like this one. Okay, and of course we can relate because we are treating with gases. If we assume that those are ideal gases, we can obtain the constant of equilibrium through using the pressure or the partial pressure of those gases, or the molar volumes too. Okay, either way, it's fine. You should obtain the same number, of course. The partial pressures, well, you can obtain it through the data, through vapor liquid equilibrium balances. But for this case, well, we can obtain them through the OSAT analysis and using theory. Okay, and there are other reactions, of course. The Butterworth reaction, in this case, it takes only in consideration the CO, the carbon monoxide, and the carbon dioxide. You see that here we have 2 over here in the exponent, because in the reaction it had 2 in the stoichiometric coefficient. For the water shift reaction, we have this other reaction. The water is the principal reactant, and carbon monoxide and hydrogen are the products. Okay, so all these constants, all these KPs, equilibrium constants, we need them to model the gasifiers, right? The gasificators or gasifiers. Okay, so we're going to do a couple of assumptions. We're not, just to be clear before we go further, we are not going to do right now a model about a gasifier. Okay, we're only going to give the equations and so on to reach to that conclusions. Okay, so of course the equilibrium constants, they change with temperature. Is the only property that changes the temperature. Okay, the equilibrium constant, the temperature. So there are ways to correct the values using a function that we're not going to talk about. What happened? Sorry for that. Okay, so we're not going to talk about how to model those functions in this class. Okay, but you can have a function to correct the equilibrium constants at different temperatures. Okay, so if you have the constant at temperature 0, let's say 25 degrees, you can correct that temperature using a function. Okay, the other assumption is that in the model we're only going to deal with ideal gases, so we're not going to use fugacities or any other kind of real gas. Okay. And we are assuming that the high temperatures are going to keep all compounds above their critical condition. If you remember, the critical condition of any substance in a diagram of pressure and temperature is this point over here, right? After that particular point, after that pressure and temperature, we can't condense a vapor into a gas. Who are you talking to, Samantha? You're joking. Okay, so
sorry.
No, it's fine. Just joking. Okay, so that one. Any questions for the moment? It looks like Ian doesn't like to use audio. The fugacity, Ian, is a way to model real gases. If you remember in chemistry and in thermodynamics, you used an equation. I don't know if you take thermodynamics, you guys. Right? You do? Yeah. Okay.
Yes.
Okay, so you should have seen the ideal gas equation and many ways to correct the ideal gas equation, like the van der Waals equation or the compressed ideal equation and so on. Okay, but if you want to model them more correctly, let's say, you have to use a property that is called the fugacity. The fugacity, if you have an ideal gas, it's the same as the pressure. But if you have a real gas and the gas is if the gas behaves non-ideally, you have to use fugacities for it. And those fugacities, well, they change depending on the properties of the gas. You can model them through many different theories, okay, that they pay attention to the size of the molecule, the polarity of the molecule, the interaction between atoms, and so on. Okay, but this particular model doesn't matter that much. No, okay, so now. Okay, so another things that in the plots that we're going to see in a couple of slides, they take into consideration is that the thermodynamic data of each compound is they obtain it in a book that is written by Patty. It has a lot of thermodynamic properties of each component. A little bit old, but it's fine. Judgment of cure for the CP of each compound. So they used the exponential function for each CP, for each specific heat. For carbon, the properties of graphite is used instead of diamond, of course, because we burn diamonds all the time. So it's of course a good proposition to use the graphite instead of other things. The heat of the fusion of the ashes is taken into consideration. Okay, so we're going to have a delta HF for the ashes. Okay, and then the fuel supply, the elemental composition of the fuel is needed. Of course, you need to have, well, for example, what you did with the biomasses in the first exam and the information that you used for the second exam. Right, that you have the composition, the elemental composition, how much carbon, how much hydrogen, how much oxygen, and so on. And the higher heating value and lower heating value is needed too for the model. So that one should be obtained before. If you don't have it, of course, it can be estimated with a long equation or any other method that you want. And the moderator in this case is the moderator is a gas that we inject into the process or into the system, so it can heat the solution and give oxygen to the combustion section and so on. And we can many times we use nitrogen as a moderator gas, and the steam should be around 300 to 400 degrees. Okay. Sorry. Okay. So other things to take into consideration in the model to see, so you can see how complex it is to do a model about a complicated process like this gasificator with 6 reactions, is that we need the balance of carbon, the hydrogen for oxygen. We need Dalton's equations for the partial pressures of each component. We need to do an energy balance, so that takes into consideration if we need to vaporize any of the components, we need the enthalpy of it. We need the sensible enthalpy to heat, to know how much heat is going to absorb each component. We need the reaction constant that you can obtain in a lab. And if you have a real fuel, most of the fuel has sulfur, nitrogen, and ashes. So we need to take those into consideration for the model to be correct. And argon sometimes, because matter fuels many times has a little bit of argon, almost nothing, but yeah, it's good to have it into consideration. Okay, so if you take all these things and put them into a model, you obtain, well, you can obtain data to see how the system behaves, right? So in this next slides, I'm going to show you well, different plots on how the systems behave, how the gasification behaves, right? Okay, so let me do that like that. Okay, so here we have what happens, how much energy we need if we compress or we don't compress the gases inside of the reactor. Okay, so the energy needed for pumping for the compressors. Sorry, yes, I have a chat over here. Can you put the two previous? Yes, of course. I'll be back in a second, guys. Just that one, I suppose. I'm going to blow the presentation, of course, to Blackboard. That was the one as well. Just that one. Okay, I suppose yes. Okay, so many times we could say that we're using too much energy, for example, to raise the pressure inside of the gasifier, right? But here we have a comparison between the same system with two different pressures. In the first one, we use a pressure of 5 bar. Okay, 5 bar is around 5 atmospheres. Okay, so here we have the energy to pump the energy we need for the compressors and for the oxygen and for the syngas. Okay, so we need around 22.58 megawatts of energy, right? But if we compress it to a 50 bar, we're going to see that we are going to use only like 1/4 of that energy for the compression, because we're going to obtain more energy in the final products. Okay, so it doesn't matter to use high pressures in this particular process. You're not going to use more energy just because you raise the pressure, because you're going to obtain more pressure, right? So high pressure reactors, they are common, okay, and we can use them, of course. If you want to use a gasifier in a low income population, you can use atmospheric pressure gasifiers. Of course, they are not as efficient as high pressure gasifiers, but they do fine, and you can reduce wastes of of biomasses that are just getting rid of instead of being used. Okay. This other plot is how a pressure change at 1000 Celsius changes the composition of the gas, right? So the main things that we want are carbon monoxide, that is the squared one, and hydrogen, that is the triangle one, right? So if you see, when we raise the pressure, like we saw in the reactions, we're going to start to diminish the amounts of hydrogen and carbon monoxide that we have, right? At low pressure, at 1 pressure, we obtain 60% of carbon monoxide, but at 100 bars of pressure, we obtain only around 38% of carbon monoxide. Okay, so it's good to use low pressures to obtain high yields of carbon monoxide and hydrogen. The only point is the speed of it, right? And if you raise the pressure, you're going to start seeing all other components. That is water, that is carbon dioxide and methane, right? So that is not ideal, of course. We should try to have as high as of carbon monoxide and hydrogen as we can. Okay, so another comparison, in this case using 1500 Celsius, right? Again, we have a different pressures, and we see again that if we have low pressure, we have high amounts of carbon monoxide and hydrogen, right? And low concentrations of all others. If we raise the pressure to 100 bars, we're going to keep high yields of carbon dioxide and hydrogen, and we're going to well, have a little bit of methane and a little bit of water and a little bit of CO2, but it's not as it's not as bad as was in the previous case at 1000 Celsius, right? So again, the equilibrium and the kinetics matter, right? So in this case, we raise the temperature to 1500 Celsius, and with that, we obtain high amounts of carbon monoxide and hydrogen, the main products, and at high speeds, right? Because well, we have a high pressure. Any questions for the moment, guys?
So it is better to put some pressure because you're going to save then energy, or
okay, yes. In that case, too, for the use of energy in the compressors, yes, you're not going to waste more energy by using high pressures, right? Because you're either going to compensate it with energy produced. Okay. Then the other two slides, the comparison is between the temperature, right? If you have not as high temperature, 1000 Celsius, the fractions of carbon monoxide and hydrogen are very dependent on the pressure. You see the difference, right? From 60 to 38% for carbon monoxide. But if you have higher temperatures, 1500 Celsius, that doesn't matter that much anymore. Okay, the high temperature compensates for the additional pressure that you are having on your system. Okay, so the ideal case from these two plots is to have high temperatures around 1500 Celsius and to have high pressures, right? Yep. Any other questions? Yep. Okay. So and then here is the comparison with the temperature. Okay, we said when we saw the reactions that high temperature for all the reactions, right? Only for methane. Methane was the only one that didn't need high temperatures. Okay, so here you can see at 30 bars, at constant 30 bars, how a gasifier behaves, right? So at high temperature, well, at low temperature for this process at 1000 Celsius, you obtain around 48% of carbon monoxide, and if you raise the temperature all the way to 1500, you see that you have a higher amount of CO produced, right? And you can see that this line starts to be more like a constant, right? It appears that raising the temperature beyond 1500 Celsius doesn't matter that much for the production of carbon monoxide, right? So that's why that's the limit in this particular plot, right? Why elevate the temperature more if you are not going to obtain a lot more of carbon monoxide, right? And then for the other components, for hydrogen, you have almost a constant plot. You have maybe the highest point is this one over here, around 1200 Celsius, but it's not a very high difference. It's almost constant, right? And for all the other products, for methane, for water, and for carbon dioxide, raising the temperature, because these are produced in exothermic reactions, raising the temperature makes the reaction to go to the left of the reaction, to the reactants, and then we don't produce those, okay? So here around 13,000 Celsius, we have almost the lowest amount possible of carbon dioxide, methane, and water, right? Okay. So that's how we can obtain the ideal conditions for the gasifier using a model like this one, making variations of temperature or pressure, more or less like we did with the AICM, right? We have an independent variable, we have a dependent variable, and then we see what is going on, right? And we can choose the best case scenario for the gasifier. This one, what we see here is the difference on how much oxygen we put inside of the gasifier, right? So here is the mole of oxygen per mole of carbon that we have in the gasifier. And here we have the mole of steam, the mole steam per mole of carbon, right? So we want this value, the y-axis, to be as high as possible, of course, okay? And we want the mole oxygen per carbon. Well, it doesn't matter exactly at what point it is, as long as it's the highest amount, right? So for example, we saw that we can obtain a lot of CO and hydrogen using 1500 Celsius, right? So if we want the highest amount of steam, we can obtain it using let's say 0.625 moles of oxygen per mole of carbon. So with this plot, we can say we can tune in the amount of oxygen that we inject. The amount of oxygen is important because remember that we are dealing with 3 different processes and they need different amount of oxygen in each part, right? We have the part with the pyrolysis that we don't need any oxygen at all. We need the part of the combustion that we need as much as oxygen as we can, so the reaction is completed. And the reduction section or the reduction zone where we want to do the reduction of the carbon dioxide and water. And in those we need well, like how to say it, like partially oxygenated system, right? So in this plot we can see at what point it would be easier to have a high conversion, right? And we could know the amount of oxygen that we need in the fuel that we have. And those are the 2 reactions that have taken place, right? We have seen them. Okay, so now we go into how a gasifier works, right? Okay, so in this gasifier, this is one of the easiest types of gasifiers. We're going to do an activity about gasifiers. So this one is the easiest one, okay? So what we have here is a container that can be, well, I have seen gasifiers even in a trash can, the big containers, even in one of those, right? You have to meet a couple of things in the design, but it's not too much. So at the bottom, we have an inlet of air, right? And here we have this dotted line over here. This dotted line is like a grill to sustain the biomass or the fuel that you're using, right? And it needs to have holes for the air to go in and the ashes to go to the ash pit, okay, that is below. Okay, so in the first section, we're going to have the combustion zone, right? So there we have a lot of air, right? That is in the first contact with air with the fuel. Okay, so there we have the combustion zone. And then the temperature is going to be high, but we're going to have low, here we have low O2, right? Low oxygen in that zone. So in that zone, the reduction can take place. We have high energy because the combustion zone gives us a lot of energy. And now we can use that energy to do the reduction of the carbon dioxide and water. And at the top of the gasifier, we obtain a gas that is CO, hydrogen, and a couple of CO2 and a couple of other things. This gasifier is not the ideal case because you obtain a dairy syngas that is cold. If you remember when you did your mental map, you found that you obtain a syngas, right? A syngas is a mixture of CO and hydrogen, right? And because this gas that we obtain here is not just carbon monoxide and hydrogen, we have a little bit of CO2 and other components, we call it a dirty syngas. Okay. So this one is the easiest one to do, of course. The lid over here should be closed completely, because if not, oxygen is going to get in those holes, and if that happens, well, you start having not just the reduction, if not continuing the combustion, and that is not the ideal case, because if not, we don't obtain carbon dioxide, of course. What time is it, guys? I don't have a watch with you.
5 y 7, prof.
Okay, so we have enough time. Okay, so we have. Okay, so this one, in which we obtain the syngas, is with carbon. Okay, with carbon, charcoal only. Okay, if we use the same gasifier, but in this case now with biomass, we're going to have the same thing. We have the mesh, we have the container, we have the gases, and so on. But here we're going to have the combustion zone. So the biomass is going to get in from the top. So we're going to have a lot of biomass over here, right? The gasifier is completely.
Hola. We can't hear anything. Rodrigo.
Rodrigo, creo que tu micrófono se volvió a apagar como la otra vez. ¿No?
Nos tiene.
No, pues duro que contestes si su micrófono está apagado.
No se mueve, ¿ves? No sé, pero estaba escribiendo.
Pero la vez pasada pasó, sí se acuerdan. O sea, sí se veía el cursor, pero no se escuchaba.
Oigan, pero que no se acababa las 5.
No, es de 4 a 5 y media, ¿no? Es como clase normal. Diana, ¿tienes algo mejor que hacer?
Tengo que acabar el examen de este Sergio.
Sergio!
Cierto.
Pero es para el sábado, ¿no?
Sí.
Lo iba a hacer hoy porque mañana no voy a poder ni el sábado.
Do you hear me now?
Yes.
Okay. Sorry for that. It's because I use my cell phone as a webcam because my desktop computer is a little bit old, so I don't have a webcam. So sometimes
¿Computadora sin webcam?
it's a desktop computer. So yeah, it's an old monitor without
De
webcam.
los 90s.
No tan vieja. Solo es como del 2010.
Windows 98.
No, sí lo actualicé, Bueno, entonces dejé. Diana, antes, ya que dijiste que si esto no se acababa a las 5. La nueva versión de las cosas según la rectoría del TEC es que pues ya se acostumbraron a esto a las clases virtuales, entonces ahora que ya se puede dar toda la hora y media.
Miren.
Mire usted.
Coffee break.
Plan.
Está bien, Fran.
Bueno, igual ya casi acabamos.
Sí.
Vamos, pues. Okay, so I don't know if you heard anything about this particular gasifier. Did you? Should I begin again?
The last thing I heard was that biomass was dropped from the top.
Okay, so yeah, that one. The biomass is going to be filled by the top of it, okay? And this complete thing is going to be packed with biomass. Okay, so when we burn the biomass in the combustion zone, of course we have a lot of oxygen because air is near the bottom, right? And after most of the oxygen is consumed, it's going to go to the reduction zone with a temperature higher than 1000 Celsius. Okay, and in that reduction zone, we're going to obtain the CO and the hydrogen that we want, right? That we want. And when the oxygen depletes completely on top of the reduction zone, we're going to have a pyrolysis zone where the biomass, the new biomass that is up here, that hasn't been born or anything, it starts to decompose, right? It starts to crack into different components. And of course, if the temperature is lower than that, you're going to have here the drying zone. Here it's around 100 to 120 Celsius. And here the gas is going to be CO and hydrogen. Okay. So these two gasifiers are the easiest ones to explain because the zones are in sequence and so on. But there are many types of gasifiers. Okay, so let me. It's not very important. Okay, so for the activity, what you're going to do is in Teams you're going to explain how the different types of gasifiers are behave, or what are the how can you do the gasification in those gasifiers, and what are the reduction zones and the pyrolysis zones and so on for each gasifier. So just you are a very healthy guys and you don't smoke, but just for the people around you that smoke, you should know that in a cigarette you have a gasifier, a small gasifier. That when you burn it in the tip of it, you have, of course, the combustion that fuels all the other reactions, right? So after the combustion, with a little bit of oxygen in this space, you have the reduction, so the production of carbon monoxide, that is a poisonous gas, and hydrogen, that doesn't matter. Then we have the pyrolysis, where you form alkitran and those kind of things. Have you seen the lungs of a smoker, that they are black? Well, that is why, because in the pyrolysis you form charcoals and tars that are components that are very, like I said in the beginning, very sticky. So if those go into the lungs, well, you have a problem in there. And then it's the drying zone, and it doesn't matter because it only produces water vapor, right? So this is the cool part. This is the not so cool part. And this is the poisonous part. No, poisonous part. I don't remember how to write that down. So that one, it's poison. So if you have somebody that smokes, let him know that he's doing a very bad thing. And the problem is that this happens with anything that you burn. Grass, marijuana, cigarettes, whatever that you burn, it does the same thing. So just a quick healthy issue. Okay, so I'm going to show you this diagram about a downdraft gasifier, but I'm not going to explain it too much because that will be the job of some team, one of the teams that we're going to do for that particular activity. Okay, so in this one, what you have is you have the biomass inside of. You have the biomass. Wait, my chat. I didn't understand Ian, your comment. So in this part, you're going to have a combustion zone here, where you have all the biomass that is getting inside because you have biomass in this section. Well, it's going to give energy to the reduction zone, and the pyrolysis zone doesn't have oxygen, and so on, right? So I'm not going to explain it. Well, you will have to explain it. So let me. I think that was it. There is another one that is called a cross draft gasifier, and there are many others. Okay. So let me change to the activity so you can see it and I can explain it a little bit.
Rodrigo.
So
Es para el próximo miércoles la actividad, digo, para la próxima semana la actividad, ¿verdad?
Oh, let me explain.
Okay.
Give me a minute. Okay, so the activity is going to be, we're going to do it next, we're going to do it next class, the first hour of next class, also on Monday, because I know that you have an exam for me and that you have other exams, and I'm not a bad person, a little bit, but not too much. Okay, so this activity, we're going to do it in the classroom, okay? Well, not in the classroom, in the Zoom room, okay? Sorry for that. So what we're going to do is that the teams, in teams of 2 or 3, depends on how you want to do them, you're going to do a presentation about one type of a gasifier, okay? You're going to have around 15 minutes to present, so it's going to be the last part of the next class, so the last half an hour, and the next class that will be on Thursday. And you're going to have different gasifiers. There is the updraft fixed bed, the downdraft fixed bed, the drain flow, the bulk fluid side bed, the circulating fluid side bed, the dual fluid side bed, and the plasma bed. Well, the plasma gasifier. Okay? And for those, the objective of the previous series is to understand the variations between the different types of gasifiers and how to perform the gasification variables. For each type of gasifier, you have to develop the following points. There is a brief history, the diagram of the device indicating the reaction regions. The reaction regions are these kind of things, right? The drying, where is the drying zone in that particular gasifier, where is the pyrolysis zone, where is the reduction zone, and so on. Okay, that is very important. And then the specific conditions. The specific condition of how we feed the gasifier, if it has a restriction on what is the type of matter that can be gasified, the type of oxidant that is used. Most of the time is air, but it can be other things. What temperature ranges we need, and what kind of things we're going to obtain, and how we're going to supply the heat. And other things, I'm sorry, the operating pressure should be the number E. This one, sorry, I will change it. It should say E. Sorry, I will change it before loading it. And then you have to give concrete examples in the industrial gasifiers, okay? What performance are expected, and what operation condition they use, and what they use the CO and the hydrogen produced to, right? And a couple and a conclusion, okay? So that, as I said, we're going to do it next class. You can start thinking about it if you want to, but I know that you are having other stuff in your mind right now. So that is the activity, and that was the class about gasification. Any questions about it?
We have a question about the exam.
Aha.
So to use the biomasses in the IECM software, how do you do that?
Well, you go to the fuel tab and you change the fuel, right? You have the percentages that you know you have on your biomass, so you change those.
Okay, yeah, we guessed it was something like that, but we wanted to ask.
Yeah, like that. Any other questions of anything? Okay.
Nope.
Well, for that one. Then see you on Monday, guys. Have a good weekend.
Bye.
Thank you.
Gracias.
See you.
Bye, Rodrigo.
Bye.
Gracias.
Inadam.